Now that we understand stream ciphers, we're going to move on and talk about a more powerful primitive called a block cipher. So a block cipher is made up of two algorithms, E and D. These are encryption and decryption algorithms. And both of these algorithms take as input a key K. Now the point of a block cipher is that it takes an n-bit plaintext as input, and it outputs exactly the same number of bits as output. So it maps n bits of input to exactly n bits of output. Now there are two canonical examples of block ciphers. The first one is called triple des. In triple des, the block size, namely the number of input bits, is 64. So triple des will map 64-bit blocks to 64-bit blocks, and it does it using a key that's 168 bits long. We're going to talk about how triple des is built in the next segment. Another block cipher, which is more recent, is called AES. Now AES has slightly different parameters. So here the block size is 128 bits. So AES will map 128 bits of input to 128 bits of output. And it actually has three possible sizes of keys, and I wrote down these sizes over here. Basically, the longer the key, the slower the cipher is, but presumably the more secure it is to break. And we're going to talk about what it means for block ciphers to be secure in just a minute. Now, block ciphers are typically built by iteration. They take in as input a key K. For example, in the case of AES, the key could be 128 bits long. And the first thing that happens to the key is it gets expanded into a sequence of keys, K1 to Kn, called round keys. Now, the way the cipher uses these round keys is by iteratively encrypting the message again and again and again using what's called a round function. So here we have this function R that takes two inputs. This function R is going to be called a round function. It takes as input the round key, and it takes as input the current state of the message. So here we have our input message. Say for AES, the message would be 128 bits exactly, because each block in AES is exactly 128 bits. And then the first thing that happens is we apply the first round function using the key K1 to the message. And we get some new message out as a result. Then we take this message M1, we apply the next round function to it using a different key, using the key K2, and we get the next round message out. And so on and so forth until all the rounds have been applied. And then the final output is actually the result of the cipher. And again, this would be also in the case of AES, this was 128 bits. And the resulting ciphertext would also be 128 bits. Now, different ciphers have different number of rounds, and they have different round functions. So for example, for triple des, the number of rounds is 48, and we're going to see exactly how the round function for triple des works. For AES, for example, the number of rounds is only 10, and again, we're going to look at how the round functions for AES work as well in just a minute. Before we do that, I just wanted to mention performance numbers. So you can see here, these are the performance numbers for the two typical block ciphers, triple des and AES. And these are the corresponding numbers for the stream ciphers that we looked at in the previous module, RC4, Salsa, and Sosa Manuk. And you can see that the block ciphers are considerably slower than stream ciphers, but we'll see that we can do many things with block ciphers that we couldn't do very efficiently with constructions like RC4. Now my goal for this week is to show you how block ciphers work, but more importantly, I want to focus on showing you how to use block ciphers correctly for either encryption or integrity or whatever application you have in mind. So to show you how to use block ciphers correctly, it actually makes a lot of sense to abstract the concept a little bit so that we have kind of a clean abstract concept of a block cipher to work with, and then we can argue and reason about what constructions are correct and what constructions are incorrect. And so an abstraction, it's a very elegant abstraction of a block cipher, is what's called a pseudorandom function and a pseudorandom permutation. So let me explain what these things are. So a pseudorandom function basically is defined over a key space, an input space, and an output space. And all it is basically a function that takes a key and an input as inputs and outputs some element in the output space. Okay, so it takes an element in K, an element in X, and outputs an element in Y. And the only requirement essentially is that there's an efficient way to evaluate the function. For functions, we're not requiring that they be invertible, we just need them to be evaluatable given the key and the input X. Now, a related concept that more accurately captures what a block cipher is called a pseudorandom permutation. So a pseudorandom permutation is, again, defined over a key space and then just a set X. And what it does is it takes an element in the key space and an element in X and outputs basically one element in X. Now, as usual, the function E should be easy to evaluate, so there should be an algorithm to evaluate the function E. But more importantly, once we fix the key k, it's important that this function e be one-to-one. In other words, if you think of the space x as a set here, and here's the same set x again, then basically the function e, what it does is it's a one-to-one function, so every element in x gets mapped to exactly one element in x. And then because it's one-to-one, of course it's also invertible. So given some output, there's only one input that maps to that output, and the requirement is that there's an efficient inversion algorithm, call it D, that given a particular output, will output the original preimage that mapped to that output. So really a pseudo-random permutation captures very accurately and syntactically what a block cipher is, and often I'll use the terms interchangeably, either a block cipher or a pseudo-random permutation. I'll use whichever term depending on the context where we're discussing things. Okay, so we have two examples, as we said, of pseudo-random permutations, triple des and AES. Say for AES 128, the key space would be 128 bits, and the output space would be 128 bits. For triple des, as we said, the block size is only 64 bits, and the key size is 168 bits. Okay, so we'll use these running examples actually throughout, so whenever I say a PRP, concretely you should be thinking AES or triple des. Now one thing that I wanted to point out is that in fact any pseudo-random permutation, namely any block cipher, you can also think of it as a PRF. In fact, a PRP is a PRF that has more structure. In particular, PRP is a PRF where the input space and the output space are the same, so x is equal to y, and in fact is efficiently invertible once you have the secret key k. Okay, so in some sense, a PRP is a special case of a PRF, although that's not entirely accurate, and we'll see why in just a second. So far we just described the kind of the syntactic definition of what is a pseudo-random permutation and a pseudo-random function. So now let's talk about what it means for a PRF or a PRP to be secure, and this concept will essentially capture what it means for a block cipher to be secure. Okay, so this is why I wanted to show you these definitions before we look at actual block cipher constructions, so at least it's clear in your mind what it is we're trying to construct. Okay, so here we have a PRF, and I'm going to need a little bit of notation, not too much though, so I'm going to need to define the set funds of x, y. This is basically the set of all functions from the set x to the set y. Denoted here as a big circle, funds of x, y. Now this set is gigantic. Its size is basically, the size of y to the size of x. So for example, for AES, remember both x and y would be 2 to the 128. So for AES, the size of the set is enormous. It'll be 2 to the 128 times 2 to the 128. So it's kind of a double exponential. So this is a gigantic number. This is more particles than there are in the universe. But regardless, we can kind of think of this set abstractly. We never have to kind of write it down. We can just keep it in our head and not worry about computing on it. So this is a particular gigantic set of the set of all functions from x to y. Now we're going to look at a much smaller set of functions, namely I'll call this set S sub f, and that's going to denote the set of all functions from x to y that are specified by the PRF as soon as we fix a particular key k. Okay, so we fix the key k, we let the second argument float, and that basically defines a function from x to y. And we're going to look at the set of all such functions for all possible keys in the key space. Okay, so if you think about it again, for AES, if we're using 128-bit keys, the size of this, I'll say SAES, is basically going to be 2 to the 128. So much, much, much smaller than the set of all possible functions from x to y. And now we say that a PRF is secure basically if a random function from x to y, so we pick some arbitrary function in this gigantic set of all functions from x to y, and we say that the PRF is secure if in fact a random function from x to y is indistinguishable from a pseudo-random function from x to y, namely when we pick a random function from the set SF. Okay, so more precisely, basically, again, the uniform distribution on the set of pseudo-random function is indistinguishable from the uniform distribution on the set of all functions. Let me be just a little bit more precise, just to give you a little bit more intuition about what I mean by that, and then we'll move on to actual constructions. So let me be a bit more precise about what it means for a PRF to be secure. And so what we'll do is basically the following. So we have our adversary just trying to distinguish truly random function from a pseudo-random function. So what we'll do is we'll let him interact with one of the two. So here in the top cloud, we're choosing a truly random function. In the bottom cloud, we're just choosing a random key for a pseudo-random function. And now what this adversary is going to do is he's going to submit points in x. So he's going to submit a bunch of x's. In fact, he's going to do this again and again and again. So he's going to submit x1, x2, x3, x4. And then for each one of those queries, we're going to give him either the value of the truly random function at the point x, or the value of the pseudo-random function at the point x. Okay, so the adversary doesn't know which one he's getting. By the way, for all queries, he's always getting either the truly random function or the pseudo-random function. In other words, he's either interacting with a truly random function for all his queries, or he's interacting with a pseudo-random function for all his queries. And we say that the PRF is secure if this poor adversary can't tell the difference. He cannot tell whether he's interacting with a truly random function or interacting